I'm Greg Gay, Assistant Professor at the University of South Carolina. As I'm recording this, Hurricane Matthew is about to make landfall in Florida. South Carolina is coming up soon after, which might make it impractical to travel this weekend to present to you in person. So if you're watching this at the conference, I'm sorry I couldn't make it up there to talk to you myself. Still, this video should give you an idea of what I've been up to, and my contact information is at the end if you have any questions. So without further ado, software powers our society. Our phones, our computers run on software. Our cars run on software. Our power grid, our transportation systems, our factories, all software. Through medical devices, software even powers our bodies. We must produce reliable, robust software. Testing is invaluable in that quest. Yet at the same time as software complexity grows, testing only grows more expensive as well. The cost of testing, however, can be traced to the manual effort required in testing activities, in jobs such as producing input and expected output. Automation could relieve that cost. One avenue is search-based test generation, which, as the name implies, treats test generation as a search problem. The exact process varies between algorithms, but in general you create a population of test suites, you score each of them based on the attainment of goals, and you use that feedback from those scores to reformulate the population, evolving it over time toward optimality. Now, even if search-based generation is fast and efficient, which it generally is, it will only be used in practice if it's at least as effective at fault detection as manual test creation. And there is little empirical evidence for that effectiveness. Much of what's out there is based on mutations, on synthetic faults automatically inserted into the code. And the jury is still out on whether mutant detection correlates to fault detection. So really a better benchmark might be whether generated tests detect real faults. And this is where Mockito comes in. Mockito is a framework for creating mock objects, objects that simulate the behavior of other objects. This is very useful, among other things, when you're testing, because Mockito can create mock objects that substitute for the dependencies of the class under test. Because you are mocking those dependencies, you know they will give the correct information to the class under test. This allows you to test that class in isolation. Mockito has seen widespread use in the Java world. One study named it the 4th most used Java library in the world. Mockito serves as an interesting benchmark for two reasons. First, it is a complex project. Much of its functionality is, naturally, related to the creation and manipulation of these mock objects. The inputs required by many Mockito functions are complex objects, which are difficult for many test case generators to produce. Second, Mockito is a mature project, having undergone 8 years of active development at this point. Recent Mockito faults are unlikely to be the simple syntactic mistakes modeled by mutation. Faults that emerge in the mature project are more likely to require specific, difficult-to-trigger combinations of input and method calls. If a test generation tool can detect such faults, then it is likely ready for real-world use. If not, then by studying those faults, and others like them, we may be able to learn lessons that will in turn improve these tools. Now, how can we get to those faults? Well, the key lies with the Defects Forge fault database. Defects Forge is a collection of 357 faults from 5 open-source Java projects. This also includes support for test generation, for coverage measurement, and for fault detection measurement. Now, all faults in the Defects Forge database meet 3 properties. First, the fault must be related to the source code. For each reported issue, we need to identify a pair of code versions that differ only by the minimum changes required to address the fault. The fixed version must be explicitly labeled as a fix to an issue, and changes imposed by the fix must be to the source code, not to other project artifacts like the build system. Second, the fault must be reproducible. At least one test must pass in the fixed version and fail on the faulty version. And third, the fix to the fault must be isolated from unrelated code changes such as refactoring. If a fault meets these 3 criteria, then it may be added to the database. Now, importantly for our purposes, Defects Forge can be extended through a partially automated fault extraction process. So we've added Mockito as a new Defects Forge project. This consisted of developing build files that work across project versions. extracting candidate faults, ensuring that each candidate could be reliably reproduced, that at least one test, again, passes on the fixed version and fails on the faulty version, and minimizing the patch used to distinguish fixed and faulty classes to remove any unnecessary changes. Now in 2014, Mockito migrated to GitHub from Google Code. While the GitHub contains the entire 8-year version history, it only contains bug reports from the past 2 years. The old Google Code issue tracker is still online, but we focused on more recent issues so that we could really focus on that maturity aspect of Mockito. These faults, they're unlikely to be easy to detect. Following this process, we extracted 17 faults from a pool of 89 candidates. Now 6 of those 17 were false positives. These were fixes to issues reported in the old issue tracker that shared an ID with issues in the newer tracking system. Now, despite that overlap, these 6 faults were valid faults and they met reasonable system maturity and complexity thresholds, so we also added those in to Defects Forge. So as an end result, we've added 17 faults from Mockito to Defects Forge. So recent studies have assessed the capabilities of test generation tools on faults in open source projects, but more data is needed to understand where such tools excel and where they need to be improved. In this study, we have generated tests using the SearchBased EvoSuite framework on classes from the Mockito project. So now that we have these 17 faults, well, we want to know A, can EvoSuite detect them, and B, what factors prevent fault detection? So for each fault, we have generated tests on the fixed version of the fault-affected classes and then applied them to the faulty version. This was done to eliminate the oracle problem. If a test passes on the fixed version and fails on the faulty version, then we have likely detected the fault. In practice, this simulates a regression testing scenario. To account for the non-deterministic nature of EvoSuite, we generated 30 test suites per fault. We've used EvoSuite's default configuration, a combination of 8 fitness functions. And as it may be difficult to attain coverage, we gave a 10-minute per class search budget. This is well over the 2 minutes used in most EvoSuite studies. Any tests that do not compile, that fail inconsistently, or that fail on the fixed system are automatically removed. In practice, this is less than 5% of each test suite. For each suite and fault, we measure the number of tests that pass in the fixed version and fail in the faulty version. We also record the achieved code coverage. Finally, for each undetected fault, we also examine the report and source code to identify possible detection preventing factors. So without further ado, our results. Well, only one of the 17 faults was detected, fault 2. Now this particular fault, revolving around the incorrect handling of negative time values, is an excellent example of the kind of fault that automated test generation is able to handle. The code fix adds conditional behavior to handle time input. And by covering the new branches, the tests are guided to detect that fault, and they do so in all 30 trials. Now, that said, EvoSuite failed to detect the other 16 faults, and that raises the natural question, why not? There are 5 reasons we'll talk about. There are certainly others, but there are 5 we'll focus on here. First, while EvoSuite is often able to achieve reasonable levels of coverage across Mockito classes, coverage is sometimes quite low. Take fault 12, for instance, where EvoSuite achieved about 12% line and 11% branch coverage over its objectives. Now, while coverage does not guarantee fault detection, unexecuted code is generally not going to reveal faults. One reason coverage may not be achieved is that code offers no guidance to the search tool when selecting better test suites. Many fitness functions are designed to measure the distance from optimality of generated test cases. However, it's not always obvious how to calculate this distance. The code that must be covered to detect fault 12 provides a good example of this. Both branches use the instance of operator. And without a good method of determining the distance between class types, the search devolves into a random search. To address this, we need more sophisticated concepts of distance. Second, a challenge for test generation techniques is the generation of input of complex data types. And as Mockito is all about generating objects that mimic other objects, well, naturally, many of its methods require complex objects as input. Even in cases where coverage is high, test generators may have difficulty producing the intricate, highly specific input required to detect that fault. Consider fault 13, which occurs when Mockito's verification capabilities are invoked on a method call that itself has an embedded method call within it. Triggering this fault requires generating two different mock objects, then embedding a call to one object within a call to the second. Coverage alone is unlikely to suggest such input. Rather, fitness functions that incorporate domain expertise may be needed to help generate more complex input scenarios. Or, in another avenue, promising work has been conducted using grammars to produce more complex test input. We should continue such research endeavors. Now, sometimes this gets us in even more trouble. Unit tests instantiate an object and call the methods offered by that object. At times, objects must be provided with input at the time that they're instantiated rather than at method call time, if they have no default constructor, for instance. Many of the code changes required to fix fault 3 are contained within one such method. EvoSuite not only fails to fully cover this method, it fails to invoke this method at all. In this case, EvoSuite attempts to instantiate the invocation master class, but many of these attempts fail due to invalid input to the constructor. EvoSuite cannot cover methods of an object that it itself cannot instantiate. Fault 5 revolves around an undesired dependency in the JUnit framework. Fixing this fault requires code changes. It is still a fault. Yet coverage of this code will not reveal this fault. Rather, the fault is detected when JUnit is removed from the local class path. This is an example of a fault that depends on environmental factors. In this case, the class path used to compile code. EvoSuite and other test generation frameworks do manipulate certain environmental factors, such as the file system access, but more examination of environmental factors is certainly needed in future test generation research. Now, the classes affected by fault 6 offer another interesting example. Mock objects can be configured to return different values based on the type of function input. Due to this fault, a mock can produce a value intended for certain data types when a null object is passed instead of the intended type. Now in this case, however, the fault fixing changes are primarily in methods that themselves don't require input, rather they're called elsewhere. These are methods called by Mockito's argument matchers. And because these methods do not require input, the fault can't be detected without in turn generating tests for the argument matcher classes that in turn call these methods. This is a case where we would have to indirectly call the faulty methods from another class. Under normal circumstances, EvoSuite could produce the required null input, but tests would need to be generated for the classes that do not themselves contain the faulty code, but instead call the faulty code. This is a case where consideration needs to be given to which classes are used and the dependencies between classes when we're generating tests. So we were given a challenge when entering this project, to do something interesting with Mockito. In our case, to answer a question. Given the current state of the art, can we detect real faults? And the answer was largely no. In some cases we did, in some cases we came close. However, in other cases there were some clear reasons why we were unable to detect those particular faults. So now, we'll certainly continue working on this, but we also pass this challenge on to you. Can you detect these faults? If you would like to try, if you would like to access this benchmark, head over to defectsforge.org. And we've actually been busy since this initial study. Now, rather than 17 faults, we have 38 real faults from Mockito that are part of Defects Forge, including 21 new faults mined from the Google Code Issue Tracker. This also includes support for mutation testing, for test generation, and for code coverage. Now, once again, I apologize for not being able to present to you today, but if you have any questions or want to discuss this benchmark, please contact me at greg@greggay.com. Other contact methods are also available on my webpage, greggay.com. Thank you very much.